Today we start our last unit of the year, and it's our shortest unit of the year as well. It's called Simple Harmonic Motion and Waves. Simple harmonic motion goes for the first few days, and then we'll transition to wave motion, and we'll show the connection between what we call simple harmonic motion and waves. Let me define simple harmonic motion for you first. The definition at first is not going to make a lot of sense to you until I explain it, but I'll give it to you anyways. Simple harmonic motion is motion in which the restoring force is proportional to the displacement. You guys know what that word proportional means? In any context. Pardon me? Not equal to, but you're not that far off. You're close. Okay, proportional doesn't mean equal to, but it means related to. So in other words, if x is proportional to y, and y goes up by a factor of 2, then x goes up by a factor of 2. Doesn't mean x and y are equal to each other, but if y doubles, x doubles. If y gets cut in half, then x gets cut in half. So x would be proportional to y if when you do something to y, the same thing happens to x. Now, simple harmonic motion is defined as that motion in which the restoring force, whatever that is directly proportional to the displacement. In other words, as displacement goes up, then the restoring force goes up by an equal amount. They're not equal to each other, but they're related to each other in the sense that when one doubles, the other doubles as well. All right, so what do we mean by the restoring force and the displacement? The restoring force acting on something is the force that pulls it back to its natural position. Now, let's try to think of a situation where we have a situation where there is a force pulling something back to its natural position. Okay? Right now, this remote control is sitting on the desk in a natural position. There's nothing pulling it back to its natural position. Even if I move it, there's nothing pulling it back to its natural position. Try to think of a situation, though, where there is something being pulled back to its natural position, to where it just wants to be. Yeah? Good. A spring is a perfect example of that. When you stretch a spring, you know that you have to pull on that with an applied force, but you also know that there's a force pulling back. If you let that spring go, then that restoring force pulls that spring back towards its natural position. Right? Same thing with an elastic, right? Spring and elastic act pretty much the same way. When you pull back on a spring, pull back on an elastic, there's a restoring force that pulls it back to its natural position. And that restoring force is proportional to the displacement, how much I stretch it, how far I stretch it. You guys remember talking when we did energy, conservation of energy, briefly about elastic potential energy, spring potential energy? We defined X as the displacement, not the displacement, how far it goes, but the displacement, how far it's stretched or compressed. The restoring force that pulls it back is directly related to that value of X. Okay, a spring or an elastic is a perfect example. Another one? Yep. A pendulum. Good. Perfect example as well. This is a pendulum right here. Okay, my key is on the end of this string here. Pendulum is something that has a string or something that is attached to a pivot point, and then we call it a bob on the end of it, okay? So we've got this pendulum bob, which is the keys in this case, on the end of this string, and then attached to the pivot point at the top. If I pull it back like this, it's going to swing back and forth like this, right? Now, the restoring force, this is the natural position right here. The restoring force acting on it at all times pulls it back to its natural position. And that restoring force is directly proportional to how much it's moved, its displacement. In other words, right now, there's a certain restoring force that pulls it back. Right now, there's a bigger restoring force that pulls it back because the displacement is bigger. Right now, the displacement is even bigger, so the restoring force is even bigger. Motion in which the restoring force is proportional to the displacement. Now, what does that mean for us? Like, what does that really mean for us? What does the spring that Kelly mentioned have in common with besides the restoring force is proportional to the displacement, but in terms of observing the motion, not measuring anything, but observing the motion, what does the spring motion have in common with this pendulum? When I pull the spring and then I let it go, when I pull the pendulum bob back and let it go, what do those two things have in common that we can see? without physically measuring numbers? Sorry? Sorry? It returns back? Did you say? It returns back to its normal position. In fact, it actually goes through its normal position. It returns to its normal position and then goes right through it and then goes to the other side and comes back to its normal position and then goes through it and then goes back to its normal position and so on. In other words, simple harmonic motion, motion in which the restoring force is proportional to the displacement, always results in motion that repeats itself. Okay? So you got a pendulum, like I just demonstrating here. The motion repeats itself. Why? Because the restoring force is proportional to the displacement. If you let the spring go, the motion repeats itself back and forth, vibrating back and forth, right? It dies out fairly quickly because the energy gets dissipated. But while the energy is still there, the motion is repeating itself. And why? Because the restoring force is proportional to the displacement. So we're going to define simple harmonic motion in another way. I'm putting this in italics because this isn't really the definition. Okay? This is the true definition. But this is how we can at least visualize simple harmonic motion, motion that repeats itself. Just remember that it does that because the restoring force is proportional to the displacement. Now I'm going to write down an equation here that we're not actually going to use right now. We're going to use it later on, but I want to bring it up right now because it relates to the definition of simple harmonic motion. Motion in which the restoring force is proportional to the displacement. We would say the restoring force, F, is proportional to the displacement, X. Or in other words, the restoring force, F, is equal to a constant times the displacement x. Remember that displacement x is not how far it moves, but rather it's the amount stretched or compressed. Still going to be measured in meters though. You guys remember what k is from back a couple units ago? We didn't do any problems with it, right? We're saving that till this unit. And in fact, we're not even going to do any problems yet with it. Remember what it is though? Yeah, it's a spring constant or elastic constant. Depends upon whether we're dealing with a spring or elastic. The units would be newtons per meter. And of course, F is equal to, actually technically F is not equal to Kx. F is equal to negative Kx. Because if the displacement is to the right, the restoring force pulls it back to the left. And if the displacement is to the left, the restoring force pulls it back to the right. My applied force, how hard I pulled it, is equal to Kx. But how hard it pulls back is negative Kx, the opposite direction. We'll deal with the mathematics of that later on, so don't panic about that right now. Examples. Oh, you guys gave me a few examples already, some good examples. The spring, the elastic, the pendulum. These are the three that we're going to deal with in this unit in a fair bit of detail. There's other ones as well, though. Sorry? Bungee cord, sure. Bungee cord would be an example of any, I guess in the end, an elastic, but yeah. Okay, specific examples, yeah, bungee cord. Even a hummingbird flapping its wings. A trampoline, perfect example of a trampoline. Although with the trampoline, you are dealing with something else in there as well, and that's gravity in there as it propels you upwards and then gravity pulls you downwards. So it's a little bit more complicated there, but yeah. There is restoring force is proportional to the displacement, certainly as you're stretching the trampoline. These are the three that we're going to focus on in this unit. The spring, the elastic, and the pendulum here. I want to define a couple of terms that you've already defined in our last unit, but in a slightly different context this time. Frequency was the number of revolutions per second or per unit time. Now we're just going to make it generally the number of cycles per unit time. And a cycle could be a revolution, but it could also be a back and forth motion of a spring or an elastic, or a to and fro motion of a pendulum as it's swinging back and forth like this. The number of cycles per unit time. The frequency would be equal to, not the number of revolutions anymore, but the number of cycles over the time. And of course, the units for frequency would be hertz. cycles per second, or hertz. You could also use cycles per minute or cycles per hour or cycles per day. But whenever you're doing a calculation, you want to be in hertz. Period. It's the time, not for one revolution, but rather the time generally for one cycle. Big T is equal to time, the total time over the number of cycles. And the units would be seconds. Or you could say seconds per cycle, but usually we just end up saying seconds there. What's the equation that relates the two of those together? Yeah, we just wrote a test on this yesterday, right? In the context of circular motion, but it really ends up being the same thing. T is equal to 1 over F. And that's, of course, the one that appears on your data sheet. This should be ridiculously easy for you, given what you did in the last unit. It's the frequency of an automobile engine in which the pistons oscillate. Oscillate? What does that mean? That's a big word. Sometimes physics people use big words. I don't know, maybe they want to sound really smart. Oscillate. What does that really mean? Turns, goes back and forth. So we could rephrase this. What is the frequency of an automobile engine in which the pistons go back and forth with a period of 0.065 seconds? I don't know. We probably shouldn't say go back and forth because we sound way smarter if we use the word oscillate, right? Just listen, I don't care what term you use, okay? But just understand what oscillate means. It means going back and forth. You're going to do some check and reflect questions a little bit later today, and they're going to talk about something called oscillatory motion. What do you think they mean by oscillatory motion? Back and forth motion. And what is back and forth motion? Simple harmonic motion. It's just a fancy word that says exactly the same thing as we've been saying already. All right, we would have solved this question in our last unit if the period of something going in a circle was 0.625. Now we're solving for the frequency if the period of something going back and forth is 0.065. We'll do it in exactly the same way. We're going to say F is equal to 1 over the period. It tells me the period is 0.0625. So it's just simply 1 over 0.0625 seconds. I'm going to show you a little trick on the calculator. It doesn't save you a whole lot of time for this problem, okay, but down the road, it can be very useful in some of the things that we do. Down the road in Physics 30, and one topic especially. You want to go 1 over 0.0625. Okay, we'll go again, 16. But let's show you another way to do that on calculators, okay? If you just type in 0.0625, and then hit the x to the minus 1 button, that's 1 over that number. So in our next year, when we deal with a lot of fractions, in one particular unit especially, and those fractions are almost always under 1 over something, and we end up having to add them and subtract them, okay, that little tidbit that I just taught you, x to the minus 1, becomes really, really useful. So whether you use it today or not, I don't really care, but in the end, it gives you the exact same thing as saying 1 over that number. 16 hertz, 16 cycles per second. Now, how many people drive? How many people have a driver's license here? Okay, you're driving on the road, you look at your dashboard and you can see the speed. You can see how much gas you have left in your car. You can see there's something called a tachometer in most vehicles as well. Tachometer says RPMs, revolutions per minute. Okay, that's a bit misleading because your pistons don't make revolutions. They go up and down, back and forth, back and forth, back and forth. What they really should say is cycles per minute. Okay? But that's what that is. It's a frequency. It's how many times your engine is going back and forth, back and forth, back and forth per minute. And why do they measure it per minute? It's just a more convenient number than measuring it per second. Okay, it's a more convenient number than saying this many hertz. That's all. But that's what it is. Okay, it's a frequency just like this is. They just shouldn't call it RPMs. They should call it RPC. CPMs, cycles per minute. Okay. All right. Let's take a look at these two questions real quickly on page 345. All right. If those questions are okay, let's talk specifically about one type of simple harmonic motion called the pendulum that you guys provided me with as an example here just a few minutes ago. The pendulum, as we've said before, is basically just a device that consists of a string or something like a string. The swinging ship, the flying galleon at the amusement park where you guys did your field trip a couple of weeks ago, it wasn't a string with a boat on the end of it. It was a piece of steel, right? A steel rod, basically with a boat or a bob on the end of it. But it's still a pendulum. It's a device that consists of a string or a piece of steel rod or something and a bob hanging on the end of it that swings back and forth, back and forth, back and forth. Now, the pendulum, strictly speaking, the force, the restoring force, is not perfectly proportional to the displacement. It's real close, but it's not perfect. So it's actually not a true example of simple harmonic motion, but it's very close. So we always consider it to be simple harmonic motion. Because of that, we're going to learn to analyze that pendulum. The period of a pendulum, or the period of the flying galleon swinging ship on the assignment that's due for you next Wednesday, is the time that it takes. Here, listen. I'm going to cover this up again. I'm going to swing my keys back and forth, and I'm going to say start. I want you guys to say stop when one period or one complete cycle has taken place. We know the period is the time for one complete cycle, okay? But what's one complete cycle for the pendulum swinging back and forth? Okay, you tell me when to stop, okay? I'll say start, you say stop when the period has, or when one complete cycle has taken place, okay? Start. Okay, so here and then back to here. Yeah, good. A lot of people will say the period is from here to here. What's that equal to? That's a half a cycle, so that's half the period. Okay? A cycle is defined as one complete to and fro motion. So we'd say the period is the time that it takes for the pendulum to move from one spot through the cycle back to the same spot. From one spot through a complete cycle and back to where it started. So we can start right up here and go back to here, or we can start right here and go back to here. It doesn't really matter, okay? But we have to be back to where we started. And then it repeats itself. If it's simple harmonic motion, it's going to repeat itself. All right, now that we've gone through this little activity that's found for us these different relationships between the period of a pendulum and these variables that we hypothesized or predicted might affect the period of a pendulum, let me give you the equation. We saw that it was dependent upon two things, right? Just two things. The length of the pendulum and gravity. Should be a really simple equation. Unfortunately, even though there's only two variables that affect it, it's not a particularly simple equation. T is equal to 2 pi square root L over G. 2 pi is 2 times 3.14. L is going to be the length of the pendulum, and that's always going to be measured in meters. And G is going to be gravitational field strength, which on Earth is going to be 9.81 meters per second squared. Now, you can imagine how you could get a problem involving the period of a pendulum on the moon, right? Don't know what G is? What do? Find it. You know how to find G now. Find G. If it's on Earth, just use 9.81. But if it's somewhere else or really high up on a really high mountain like Mount Everest, then find it. And then use 2 pi square root L over G. Now, we don't usually do this, but what we're going to do next with this equation before we do any problems with this is actually show you how to rearrange it to solve for the different variables, because this one gives people a lot of trouble. V equals D over T gives some people trouble to rearrange. So if you're having trouble with V equals D over T, then you're going to have a lot of trouble with this one. Let me show you how to solve for L, and let me show you how to solve for G. Here's the base equation again. If you're solving for T, easy, right? If you wanted to solve for F, it's pretty easy because we just say F is equal to 1 over T. But if we're solving for L or G, a little bit harder. Yep. Yes, you got to take the 2 pi over first. Doesn't matter what you're solving for. Take the 2 pi over first. So it becomes T over 2 pi equals square root L over G. Now, regardless of whether you're solving for L or for G, what are you doing next? Squaring it. So we're going to say T over 2 pi squared equals L over G. Now, if you're solving for L, okay, if you're solving for L, it's pretty good at this point. What do? Bring the G over by multiplying. So it becomes L is equal to G times T over 2 pi squared. Here's our first equation that's on our data sheet, and there's the second form of it solving for L. But maybe we want to solve not for L, maybe we want to solve for G. Maybe you're doing an experiment at the top of Mount Everest. You want to find out what the gravitational field strength. We know how to calculate it, right? We're in that last unit. But how do you actually measure it? Take a pendulum up to the top of Mount Everest. Swing it back and forth. Measure the period. Measure the length of it. Determine what little g is. Well, we got to rearrange this to solve for little g. How do you get rid of the t over 2 pi squared? Let's pretend the t over 2 pi squared is one term. It is. So we're just going to take it to the other side by dividing. G equals L over T over 2 pi squared. We took the whole thing over at once by dividing. And there it is. Now we could simplify that. We're not going to, because I think actually the process of simplifying it is not simple. The final product looks simple, but the process is actually quite complicated. So I think we're going to just leave it like this. G is equal to L over T over 2 pi squared. Now the only thing you got to be careful of when you're solving for little g here, besides getting the form of the equation correct here, is plugging the numbers into your calculator. Okay, we're going to do an example here in a couple minutes, but my suggestion when you're solving for, especially when you're solving for g, get 2 pi first. Then say t over that number, press equals. And then square that number, press equals. And then say L over that, press equals. Do one step at a time. Everything on the bottom first. 2 pi equals. T over 2 pi equals. T over 2 pi squared equals. L over that equals. And then you should have your answer. If it was on Earth, it should be about 9.81 meters per second squared. Okay? All right, let's do a question here. This one is a question where we want to find the gravitational field strength at the top of Mount Everest. Basically, it's the same thing as you just did with the little activity, except it's at the top of Mount Everest, not on the floor of Holy Trinity. The length of the pendulum is a meter, has a period of 2.01 seconds. We're going to say t is equal to 2 pi square root L over g. I'm going to rearrange this again, even though I just did it, because I think there's value in going through this again. The more times you see it being rearranged, the more likely you are to be able to rearrange it. I want to solve for little g, which is the hardest variable to solve for. So I'm going to take the 2 pi over by dividing, I should say. 2 pi is equal to square root L over g. I'm going to take the square root over by squaring. T over 2 pi squared equals L over g. I'm going to take the g up by multiplying. G times T over 2 pi squared. Yeah, we're looking for G, aren't we? No, we're looking for G. Looking for G, the gravitational field strength. Now I got to take the T over 2 pi squared over by dividing, and I end up getting G equals L over T over 2 pi squared. Now let's see what we get here. The length is 1 meter. T is 2.01 divided by 2 pi squared. Now I know some of you are having a little bit of trouble when you do a little activity actually using this equation in its rearranged form to calculate the value of G. Let's spend a minute going through this one now to make sure that we can all do that. We're going to start at the bottom. 2 times pi equals. If you're ever having trouble with brackets or when to do something on your calculator, always start with the bottom number first. T over 2 pi, 2 pi is 6.283. Now let's say 2.01 divided by that number. Gives me 0.3199. That's what's inside the brackets. Now I've got to square that, and I get 0.102 on the bottom. Now I'm going to say 1 over that, or what's another way of doing 1 over that? We could just say x to the minus 1 gives me 9.77 meters per second squared. Or we could have used what other units for gravitational acceleration other than meters per second squared? Newtons per kilogram, right? We learned that in our last unit when we were talking about gravitational fields, right? All right, let's have a look at these three problems on page 379 now that go along with that. And that's your homework for tonight.